Look around you right now. Look at the world outside your window, the trees, the soil, the animals, the flowers. Look at the forest floor or a meadow or a garden. Then ask yourself one honest question. Where is the blue? Not the sky, not the ocean, not those. Those are illusions we will get to, and when we do, your jaw will drop. But the actual living world, the biological world of organisms that grow and breathe and reproduce, where is the blue in that world? There is almost none. That fact is so strange, so quietly bizarre, that most people never notice it. We are surrounded by blue every single day. The sky dominates our entire visual field. The oceans cover 70% of the planet's surface. And yet, if you took every species of flower, every bird, every insect, every mammal, every reptile, every plant, and laid them all out in front of you, the blue ones would fill a corner of the room. The rest of the room and the overwhelming, crushing majority of the room would be red, orange, yellow, green, brown, black and white. Blue is the colour of our world's backdrop, and almost nowhere in its cast of living characters. Fewer than 10% of all flowering plant species produce blue flowers. Of those, the majority of what we call blue is, when tested with scientific instruments, actually violet or purple, not technically blue at all. Among animals, there's not a single mammal with blue skin or blue fur. Not one. Not a single mammal in the entire history of vertebrate life on Earth has ever evolved a true blue pigment in its skin. Among birds, the ones we call blue, the blue jay, the bluebird, the indigo bunting, the kingfisher, carry no blue pigment anywhere in their bodies. Zero. The blue you see on those birds is physically impossible to find if you look for it at the molecular level, because it does not exist as a dye or chemical. It is something far stranger. And blue eyes in humans? Also not blue. Not in the way a blue paint is blue, or a blue flower is blue. The blue eyes of millions of people contain no blue pigment whatsoever. What they contain is nothing. Literally an absence of pigment, and a trick of physics that turns that emptiness into the colour you see. This is where things start getting genuinely mind-bending. The rarity of blue in nature is not an accident. It is not a gap in evolution's creativity. It is not because blue is somehow unattractive to animals or insects. It is the result of something much deeper, a collision between the laws of chemistry, the laws of physics, and the brutal pressures of natural selection. Blue is rare because making blue at the molecular level is extraordinarily, almost impossibly hard, and when organisms do appear blue, they have usually not actually made blue at all. They have done something far more sophisticated and far more expensive. They have built tiny machines, nanoscale optical architecture, structures smaller than the wavelength of light itself, that trick photons into behaving as though blue pigment exists when it doesn't. And humans? Humans spent 6,000 years of recorded civilization desperately trying to make blue, and mostly failing. Blue was worth more than gold at multiple points in human history. Entire economies were shaped by the scarcity of blue. wars were fought over its sources. Artists who could afford blue were either very wealthy or very connected to power. The Renaissance's greatest painters reserved their blue pigment exclusively for the most sacred figures in their work, the Virgin Mary, the Christ child, because blue was so precious that using it anywhere else was considered wasteful and irreverent. The Nobel Prize in Physics was awarded in 2014 within living memory of most adults today, for finally solving one specific problem that had stumped engineers and scientists for 30 years: how to make blue light efficiently from electricity. Red and green LEDs had existed since the 1960s. Blue eluded humanity until the 1990s, and the breakthrough was so difficult, so technically brutal, so far beyond what most experts believed was achievable, that the three engineers who cracked it received science's highest honour. Think about that timeline. We put humans on the moon in 1969. We sequenced the human genome by 2003. We built nuclear reactors in the 1940s. But making blue light, blue, the colour you see in the sky every single clear day, efficiently and cheaply from a semiconductor, that took until 1993. Why? What is so special about blue that chemistry resists it, that evolution struggles against it, that physics makes it nearly unreachable, that human civilization spent millennia in frustrated pursuit of it? That is what this documentary will answer. And the answer, it turns out, touches the deepest machinery of how matter and light interact. The quantum mechanics of electrons, the geometry of molecules, the history of pigment chemistry going back to ancient Egypt, the evolutionary arms race of billions of years, and the audacious stubbornness of one obscure Japanese engineer working alone at a small chemical company that most people in his industry had never heard of. Buckle in. The story of blue is one of the most extraordinary stories in all of science. Part 2. What is colour really? Before we can understand why blue is rare, we have to understand what colour actually is, because the answer is more disturbing and more wonderful than most people realise, and unless you get this right, nothing else in this story will make proper sense. Colour is not a property of objects. Let that sink in for a moment. The redness of a red apple, the greenness of a green leaf, the yellowness of a sunflower, none of those colours exist inside the objects themselves. Colour is a relationship between light, matter, and the nervous system of an observer. It is an experience that emerges when photons of particular wavelengths interact with detector cells in the eye and generate signals that the brain then interprets, labels, and experiences as a colour. The electromagnetic spectrum, the full range of radiation that travels through space at the speed of light, covers an enormous range of energies and wavelengths. Radio waves at one end have wavelengths measured in kilometres. Gamma rays at the other end have wavelengths smaller than the diameter of an atomic nucleus. The tiny, absurdly narrow slice of this spectrum that human eyes can detect, the visible spectrum, runs from roughly 380 nanometers at the violet end to about 700 nanometers at the red end. A nanometer is 1/billionth of a meter. A single human hair is about 80,000 to 100,000 nanometers wide. The entire visible spectrum of light, the whole range of what we experience as colour, fits inside a width range narrower than the diameter of a human hair. Within that narrow band, different wavelengths correspond to different colours. Red light sits at the long wavelength low energy end, around 620 to 700 nanometers. Orange is 590 to 620. Yellow is 570 to 590. Green occupies the middle, 495 to 570. And blue runs from about 450 to 495. And violet is at the far high energy short wavelength end, from 380 to 450 nanometers. This matters enormously because wavelength and energy are directly related by a law of quantum physics. The shorter the wavelength, the higher the energy. Blue light photons carry significantly more energy than red light photons. This is not a small difference. A blue photon carries roughly twice the energy of a red photon. That energy gap is at the heart of why blue is so hard to make and maintain. Higher energy photons are harder to produce, harder to control, harder to stabilize in chemical structures, and harder to reflect efficiently through nanostructures. Every single challenge in the story of blue traces back to this one physical fact. Blue photons are energetically demanding. Now, when light strikes a material, any material, one of several things can happen. The material can absorb the photon, converting its energy into heat or chemical reactions. The material can transmit the photon, allowing it to pass through. Or the material can reflect the photon, sending it back toward the observer. The colour that an observer sees is determined by which photons are reflected. A red apple appears red because its skin contains pigments that absorb virtually all photons except those in the red wavelength range, which are reflected into your eye. A green leaf appears green because chlorophyll, the molecular workhorse of photosynthesis, absorbs red and blue light, uses that energy to drive chemistry, and reflects the leftover green. Pigments are molecules that selectively absorb specific wavelengths of light. The key word is selectively. A good pigment doesn't just absorb everything. It absorbs particular wavelengths based on the architecture of its molecular structure, specifically the arrangement of electrons in its chemical bonds. When electrons in a molecule are excited by incoming photons, they jump to higher energy states. Different molecular architectures require photons of different energies to cause this excitation. A molecule that absorbs red photons carrying about 1.8 electron volts of energy, to excite its electrons will appear blue or green or violet, the colours whose photons are reflected rather than absorbed. A molecule that absorbs blue photons carrying about 7 electron volts, will appear orange or red or yellow. This is crucial. A blue pigment is a molecule that absorbs the complementary colours, reds and yellows, and reflects blue. To do that efficiently and stably, it needs to have a molecular structure in which electrons can be easily excited by the relatively high energies of red photons, while reflecting the even higher energy blue photons without absorbing them. That turns out to require a very specific kind of molecular geometry, one that is, chemically speaking, difficult to build and difficult to maintain. There is another way to produce colour, though, that bypasses pigment chemistry entirely. This is called structural colour. and it is the secret behind the blue of butterflies, birds, sky, and human eyes. Instead of relying on a molecule's electronic structure to absorb certain wavelengths, structural colour uses the physical geometry of a surface or medium to cause constructive interference of specific wavelengths of light. This is the same phenomenon that makes oil slicks rainbow-coloured and soap bubbles shimmer, when light waves reflect off two different surfaces separated by a very small, precisely controlled distance. The reflected waves can add together constructively at some wavelengths and cancel each other out destructively at others, creating vivid wavelength-specific colour without any pigment at all. Nature, it turns out, has become a master engineer of structural colour. And the blue wavelength, with its short, precisely controlled distance requirements, is both the most challenging colour to produce through structural means, and, in some organisms, the most spectacular result. Understanding both pathways, pigment chemistry and structural physics, is necessary to understand the full story of why blue is rare. Because both paths are difficult for blue, and both paths have their own extraordinary history of failure and ultimate breakthrough. Part 3. The chemistry of colour, and why blue molecules are rare. Life runs on chemistry. Every colour in the biological world, the red of blood, the orange of a tiger lily, the black of a raven's wing, the green of every leaf on every tree, is produced by molecules. And those molecules are produced by the metabolic machinery of cells, built from simpler chemical building blocks following instructions encoded in DNA. The most widespread colour-producing molecules in nature fall into several major chemical families. Chlorophylls give plants their green. Carotenoids produce the reds, oranges and yellows of fruit, autumn leaves, egg yolks, and the skins of carrots. Melanins produce the browns and blacks of skin, hair, fur, and feathers. Hemoglobin gives blood its red. Bilirubin gives bruises their yellow. Each of these molecular families is either biochemically easy to synthesize, energetically advantageous to produce, or functionally indispensable to life, and often all three. Blue pigments share none of those advantages. They are biochemically complex, energetically expensive to produce, functionally marginal in most organisms, and chemically unstable under many conditions. Let us examine exactly why. The most important class of pigment molecules that touches on blue in the plant kingdom is the anthocyanins. These are water-soluble molecules belonging to a broader class called flavonoids, which are among the most widespread plant pigments in existence. Anthocyanins are remarkable molecules. They can appear red, pink, purple or blue, depending on their chemical environment. The pH of the cell, the presence of metal ions, the company of other molecules, even the temperature, all of these factors can shift an anthocyanin's colour dramatically. At low pH, acidic conditions, anthocyanins typically appear red. At higher pH, more alkaline conditions, the same molecule can shift toward purple and blue. The biosynthesis of anthocyanins is not simple. More than 5 enzymes working in perfect concert are required to produce these pigments, each one catalyzing a specific chemical step in a multi-stage pathway. The raw materials come from two different metabolic streams in the cell that must be coordinated with remarkable precision. One stream involves the shikimate pathway, which produces the amino acid phenylalanine. The other produces malonyl-CoA units. These two streams are coupled by an enzyme called chalcone synthase to create a precursor compound called chalcone, which is then transformed through a further series of enzymatic steps into the final anthocyanin molecule. Even a minor disruption in any of these enzymatic steps, a mutation in any one of the relevant genes, or an unfavorable change in temperature or cellular chemistry can halt anthocyanin production entirely. But producing anthocyanins is only the first problem. The deeper problem is making them blue. The most blue-shifted anthocyanin that has ever been identified in nature is a compound called delphinidin. Even delphinidin, however, is not truly blue in the spectroscopic sense. It occupies the violet-blue boundary, absorbing wavelengths that place it at around 380 to 430 nanometers, which technically makes it violet rather than the true blue wavelength range of 450 to 495 nanometers. The flowers we commonly call blue, delphiniums, hydrangeas, cornflowers, morning glories, gentians, are all, when measured precisely, producing violet or blue-violet colour rather than pure blue. True blue, spectrographically defined, is extraordinarily rare in any living pigment. Even achieving that imperfect violet blue through delphinidin requires the plant to do several more extraordinary things beyond just synthesizing the anthocyanin. Anthocyanins, in their natural state at physiological pH, which in plant cell vacuoles is around 5.5, are chemically unstable. They rapidly form colourless hemiketal structures, and from there they isomerize into yellow chalcone forms. In other words, a blue anthocyanin, left to its own devices at normal cellular pH, would quickly become colourless and then yellow. To stabilize blue or violet colour, plants have evolved three distinct chemical strategies, each of which adds layers of biochemical complexity. The first strategy is intermolecular copigmentation. The anthocyanin pigment molecule stacks against another class of colourless molecules called copigments, typically flavones or flavonols, through non-covalent interactions, hydrogen bonds and hydrophobic stacking forces. This association stabilizes the anthocyanin and shifts its color toward the blue end of the spectrum through a phenomenon called the bathochromic shift. Cornflowers achieve their blue this way. The anthocyanin-cyanidin complexes with a flavone copigment in a non-covalent embrace that locks the blue-violet color in place. The second strategy is intramolecular copigmentation, where the acyl groups attached to the glycoside arms of the anthocyanin fold over and stack against the anthocyanin's own chromophore ring system, protecting it from water attack and stabilizing the blue form. Japanese gentian flowers have evolved an extraordinarily complex anthocyanin, gentiodelphin, which carries 4 aromatic acyl groups and achieves a rich blue color through this mechanism. But the biosynthesis of gentiodelphin requires a suite of specialized enzymes that most plants never evolved. It is the molecular equivalent of a masterwork of engineering that took millions of years of natural selection to construct. The third strategy is metal chelation, metalloanthocyanins. In some blue flowers, anthocyanins complex with metal ions like magnesium, iron, aluminum or calcium to form supramolecular pigment complexes. The most studied example is comelanin from the dayflower plant Commelina communis, which assembles into a large, highly ordered structure containing 6 anthocyanin molecules, 6 flavone copigment molecules, and 2 magnesium ions in a precise stoichiometric ratio. The morning glory produces blue through a different metal mechanism involving magnesium and a pH change in the vacuole. Hydrangeas famously change colour depending on soil pH because the availability of aluminum ions in the soil changes. More aluminum means more blue because the aluminum binds the delphinidin and shifts its colour toward blue-violet. These metalloanthocyanin complexes are breathtakingly sophisticated, but they come at a steep price. They are only blue in aqueous solution. The colour entirely disappears during isolation or crystallization. They are sensitive to pH, temperature, oxygen, and changes in metal ion concentration. They are, in the terminology of anthocyanin chemistry, fuzzy, not truly stable, just temporarily pinned into a bluish state through a delicate balance of conditions. The bottom line of all this plant chemistry is stark and humbling. No plant anywhere in the history of plant life on Earth has ever evolved a dedicated blue pigment molecule. Not one. Every blue flower achieves its colour through modifications of fundamentally red pigments. Anthocyanins shifted toward blue through complex, energetically expensive and chemically precarious strategies that still don't produce true spectroscopic blue. There is no true blue pigment that is common or stable in living organisms. Unlike red, yellow or green, colours produced by more straightforward pigments, blue is more of an optical illusion, a trick of physics rather than chemistry. Why can't plants just evolve a true blue pigment molecule? The answer lies in fundamental organic chemistry. A molecule that efficiently absorbs red light and reflects blue, the profile you need for a pure blue pigment, requires a specific electronic structure involving extended systems of conjugated double bonds that are extremely difficult to achieve in organic molecules built from the atoms that life's chemistry prefers. The same chemical properties that would make such a molecule a good blue pigment also tend to make it chemically reactive and unstable under the conditions found in living cells. Life builds its coloured molecules from carbon, hydrogen, oxygen, nitrogen and sulfur. The molecular architectures that produce stable blue coloration in inorganic compounds, coordination compounds of cobalt, copper and other transition metals, or complex crystal structures like lapis lazuli, are simply not achievable through the metabolic pathways that cells have evolved. Furthermore, there is an additional evolutionary reason for the scarcity of blue in plants specifically. Blue light carries more energy than other colours in the visible spectrum. Plants absorb blue light efficiently for photosynthesis, so reflecting it by appearing blue means losing out on this crucial energy source. Green chlorophyll remains dominant because it reflects less energetic green light, allowing plants to maximize their energy intake. A plant that evolved blue leaves, reflecting the blue light that powers its own photosynthesis, would be at a severe metabolic disadvantage compared to its green neighbours. The same energetic argument applies, less directly, to flowers. While blue flowers do exist and do attract pollinators, blue coloration provides only a relatively niche evolutionary advantage in attracting specific pollinators. Combined, these are the principal reasons that blue pigments are relatively uncommon in nature. Insects, particularly bees, can see ultraviolet light and are generally attracted to flowers in the ultraviolet blue and yellow ranges, which creates some evolutionary pressure for blue flowers. But the difficulty of producing a stable, true blue colour is so great that most plants either produce violet approximations, use structural tricks, or simply don't bother and use other colours that are easier to make. The animal kingdom faces all of the same challenges and adds additional ones. Many animal pigments are diet-derived, like flamingos turning pink from shrimp or goldfish shimmering golden from carotenoids in their food. But since no plants produce a true blue pigment, animals can't eat their way to blue. The entire dietary pathway for acquiring blue colour is closed off, because the plants that might donate blue pigments to the animals that eat them simply don't exist. This creates a complete metabolic dead end for any animal attempting to produce blue through conventional pigment biology. Part 4. The physics of fake blue, structural colour, and the nanoarchitecture of illusion. Since chemistry can barely produce blue, and life cannot evolve its way to a reliable blue pigment, nature has resorted to a breathtaking alternative: building, at nanometer scales, physical structures that manipulate light itself. Structural colour is not produced by absorbing some wavelengths and reflecting others through molecular electronic transitions. It is produced by the physical geometry of surfaces and materials, which causes different wavelengths of light to interfere with each other in precisely controlled ways. The result is colour, produced not by chemistry but by physics, not by what molecules the organism contains, but by how it is architecturally built at the nanoscale. To understand structural colour, you first need to understand what happens when light encounters a thin layer of transparent material sitting on top of another surface. When light hits the top surface of this thin layer, some of it is reflected back immediately, but some passes through and bounces off the bottom surface of the layer, then travels back up to join the first reflected beam. These two reflected beams started as the same wave, but the second one has travelled slightly further, down through the layer and back up. Depending on the thickness of the layer and the wavelength of the light, this extra travel distance might cause the two beams to emerge perfectly in phase with each other, in which case they add together and you see a bright reflection. Or they might emerge perfectly out of phase, in which case they cancel each other out and you see nothing at that wavelength. This is thin film interference, the same physics that makes soap bubbles shimmer with rainbow colours and oil on water produce psychedelic patterns. Now imagine not one thin layer, but dozens or hundreds of them, precisely stacked, each separated by a tiny air gap, each with a thickness calibrated to the wavelength of blue light. The constructive interference of blue wavelengths builds up with each layer, reinforcing and amplifying the blue reflection, while all other wavelengths cancel themselves out. You get an intense, pure, brilliant blue, not because the material contains any blue dye, but because its geometry forces blue photons to add together while all other photons subtract. This is structural colour, and the organisms that have evolved it are, from an engineering standpoint, building optical devices of breathtaking sophistication using only the raw materials of biological chemistry. The most famous example, the one that has inspired decades of scientific research, generated hundreds of papers and launched entire fields of bio-inspired nanotechnology, is the morpho butterfly. The morpho butterfly lives in the rainforests of South America. Its wings are a blue so brilliant, so electric, so intensely vivid that it seems to glow from within. The blue is visible from 100 meters away. It shifts slightly as the angle of observation changes, shimmering with a quality that is simultaneously luminous and deep. Scientists who first examined those wings under ordinary microscopes were baffled. The wings appeared to have no blue dye whatsoever. The wing material, chemically extracted and analysed, was essentially colourless. So where was the blue? The answer required an electron microscope. When the wing scales of a morpho butterfly are examined at the nanometer scale, what you find is an architecture of astonishing complexity and precision. Each wing scale is covered with parallel ridges running along its length. But these are not simple ridges. Each ridge is itself built like a tiny Christmas tree, with multiple horizontal lamellae, or shelf-like branches extending from a central stalk. Each lamella is approximately 70 to 80 nanometers thick, roughly the same dimension as the wavelength of blue light. Between each lamella is a gap of approximately 150 nanometers filled with air. When white light, which contains all wavelengths, strikes this nano-architecture, the precise dimensions of the layered lamellae cause constructive interference of blue wavelengths, while other wavelengths cancel. The structural colour and iridescence is a product of visible light interacting with rows of Christmas tree-shaped nanostructures on the scales of these butterfly wings. These Christmas trees have anywhere from 6 to 10 alternating branches which cause light to constructively interfere between 400 and 500 nanometers in wavelength, the blue and purple range. The result is that up to 75% of the incident blue light is reflected, a higher reflectivity than almost any blue paint ever manufactured. The colour is so vivid precisely because the nanostructure is so precise. This can result in around 75% of the light being reflected in cases such as the blue morpho scale. But the morpho butterfly's nanoarchitecture is even more sophisticated than simple multilayer interference. If you had a perfectly uniform multi-layer stack, the blue colour would be highly angle-dependent. You'd see the blue only at specific angles of illumination, and at other angles it would disappear. Real morpho wings don't behave this way. the blue is visible over a remarkably wide range of angles. Why? Because the combined action of interference and diffraction is essential for the structural colour. The presence of irregular heights between adjacent ridges is extremely important, and the pigment beneath the iridescent scales greatly enhances the blue colouring by reducing the unwanted background light. The slight disorder in ridge heights, what seems like imperfection, is actually an evolved feature. It causes the diffracted blue light to spread across a wide range of angles, making the wings visible as blue from almost any direction. Underneath the iridescent upper scales, a layer of black melanin pigment absorbs any stray green or red wavelengths that manage to pass through the structural filter, further purifying and enriching the blue. This combination of multilayer thin film interference, diffractive spreading, and absorptive filtering working in concert is a feat of optical engineering that took millions of years to evolve. Attempts to replicate it in the laboratory using industrial processes, chemical vapor deposition, electron beam lithography, nano-imprint techniques, have yielded partial successes but face enormous difficulties in matching the precision, the three-dimensional complexity, and the large area uniformity that morpho-wings achieve through biological self-assembly. The morpho-butterfly is the most celebrated example, but it is far from alone. Nature has evolved structural colour independently on dozens of different branches of the tree of life, each time arriving at a different nanoscale architecture that achieves the same result. Bluebirds, including the blue jay, the bluebird, the kingfisher, the indigo bunting, the blue grosbeak, achieve their colour through an entirely different structural mechanism. The pigment in a blue jay's feathers, melanin, is brown, but we perceive it as blue because of a phenomenon called light scattering. A blue jay's wings contain tiny pockets made of air and keratin, the same protein that makes up our hair and fingernails. When light hits these pockets in the blue jay's feathers, all of the colours of the wavelength except blue are absorbed. The blue wavelength is refracted, which is what allows us to see the feathers as blue in colour. The structure inside blue bird feathers is a spongy, quasi-amorphous array of keratin strands and air pockets, built at a scale where the air pockets are roughly comparable to the wavelength of blue light. Unlike the morpho-butterfly's highly ordered crystalline structure, bird feather nanostructure is quasi-amorphous, partially disordered, but the disorder itself is controlled at a specific spatial scale that produces constructive interference of blue wavelengths, while allowing longer wavelengths to pass through and be absorbed by the underlying melanin layer. As with most other blue-hued birds, the blue jay's coloration is not derived from pigments, but is the result of light interference due to the internal structure of the feathers. If a blue feather is crushed, the blue disappears because the structure is destroyed. This is the definitive test. Crush a blue jay feather, destroy the nano-architecture, and the powder is brown. Just the melanin pigment, no longer arranged to scatter blue light, revealing what was always chemically present, nothing blue at all. If you grind up the wing of a cardinal, the resulting powder will be red. If you do the same with a blue jay feather, the powder will be brown. There are no blue pigments in birds. Every blue bird, bluebirds, indigo buntings, blue grosbeaks, lazuli buntings, their feathers all employ the same light refraction process to appear blue. All blues are a result of that. The implication is stunning. Every bird that appears blue to human eyes is built from brown melanin. The blue is entirely a product of geometric optics at the nanoscale. Human blue eyes operate by a third structural mechanism, even simpler and more surprising. The iris of a blue eye contains essentially no pigment in its anterior layer. Where there is no pigment to absorb or reflect specific wavelengths, white light enters the iris and the short-wavelength blue photons scatter off the collagen fibers in the stroma, the deep structural layer of the iris, more readily than the longer wavelength red and yellow photons, which pass through more easily. This scattering of short wavelengths preferentially back toward the observer is similar to Rayleigh scattering, the same mechanism that makes the sky appear blue. Blue eyes don't contain blue. They contain a scattering geometry that isolates blue photons from the reflected light, producing the appearance of blue from essentially nothing. The sky itself, of course, is the most spectacular example of structural colour in nature. Sunlight entering the atmosphere encounters molecules of nitrogen and oxygen. These molecules are much smaller than the wavelength of visible light, and when photons encounter objects much smaller than their wavelength, they scatter preferentially depending on wavelength. Specifically, scattering intensity varies inversely with the fourth power of wavelength. This means blue photons scatter roughly 10 times more strongly than red photons. In all directions away from the direct path of sunlight, the atmosphere appears blue because the scattered photons are overwhelmingly short wavelength. In the direction of the sun, at sunrise and sunset, when the path length through the atmosphere is much longer, most of the blue has already been scattered away, and only the reds and oranges remain, hence the brilliant colours of sunsets. The sky, in a meaningful sense, is the Earth's ultimate structural colour display, operating at scales ranging from molecular to planetary. Dragonflies achieve blue through Tyndall scattering in layers of cells near their surface. Many beetles produce iridescent blues and greens through multi-layer systems in their cuticle. The brilliant blue of some bird of paradise feathers comes from arrays of melanin granules in specific geometric arrangements. The blue of certain sea creatures arises from multi-layer thin films in their translucent tissues. Some cephalopods, squid and octopuses can dynamically change their structural colour by contracting and relaxing muscles that control the geometry of iridophores, thin film reflective cells embedded in their skin. The evolutionary convergence is astonishing. Blue structural colour has evolved independently at least a dozen times in insects, at least a dozen times in birds, multiple times in fish and other marine animals, in reptiles, in spiders, in fruit. Each time, starting from different biological materials and different genetic pathways, evolution has arrived at the same solution. Build nanostructures at the scale of blue light's wavelength to produce constructive interference of blue photons. Blue is so difficult to produce chemically that whenever natural selection has pushed organisms toward blue, It has overwhelmingly driven them not toward chemistry, but toward nanoscale architecture, the hardest possible evolutionary strategy, requiring the most precisely controlled biological construction, but the only reliable path to blue when molecular chemistry falls short. Most of what we perceive as blue in nature comes from structural coloration, microscopic arrangements that bend and scatter light to trick our eyes. These nanoscale patterns are far more difficult to evolve than common pigments, which is why blue remains so rare. Part 5. The Ancient Obsession. 6,000 years of failing to make blue. If understanding the biology and physics of blue reveals why it is rare in the natural world, then turning to human history reveals something equally extraordinary. The rarity of blue-haunted humanity for thousands of years, and the struggle to make it is one of the most dramatic stories in the history of technology and art. Start in ancient Egypt, 5,000 years ago, along the banks of the Nile. The Egyptians were a civilization of extraordinary sophistication. They built the pyramids. They mastered irrigation. They developed writing, medicine, and one of the world's first major legal systems. They had a rich and deeply symbolic visual culture, and in that culture colour was not merely aesthetic, it was theological and cosmological. Colours carried specific divine meanings. Gold was the colour of the god's flesh. Black represented the fertile silt of the Nile and by extension life itself. Red could mean life or destruction depending on context. Green symbolized renewal. White meant purity and sacredness. And blue? Blue was the colour of the sky, of the Nile at its deepest, of lapis lazuli, one of the most precious materials in the ancient world. Blue was associated with Amun, king of the gods, and later with Osiris and the afterlife. Blue was sacred, royal, and cosmically significant. It was everywhere in Egyptian religious art, temple decoration, funerary objects, and royal jewellery, which created an enormous practical problem because natural sources of blue were almost impossibly scarce. The most prized blue material in the ancient world was lapis lazuli, a deep blue metamorphic rock whose rich colour comes from a mineral called lazurite, which contains sulfur radical anions embedded in a zeolite crystal lattice. Lapis lazuli has been mined for centuries from a location still in use in the mountain valley of Kokcha, Afghanistan. First mined 6,000 years ago, the rock was transported to Egypt and later to Europe, where it was used in jewellery and paint. This single remote mine in what is today northeastern Afghanistan was essentially the world's only significant source of lapis lazuli, and it was thousands of kilometres from Egypt, requiring a trade route of extraordinary length and logistical complexity to traverse. The stone arrived in Egypt as an impossibly precious cargo, measured by weight like gold. Ancient Egyptians used lapis lazuli in solid form for ornamental applications in jewellery. However, there is no record of them successfully formulating lapis lazuli into paint. This is a critical failure. The Egyptians could grind the stone to powder, but when they did, the brilliant blue of the massive stone gave way to a dull, greyish blue, because lapis lazuli is not a pure mineral, but a mixture of lazurite with calcite and pyrite, and when ground, these contaminating minerals dilute and muddy the colour. The Egyptians tried and failed to turn it into a paint, with each attempt resulting in a dull grey. The very stone they most desired for its blue, when reduced to a paint pigment by simple grinding, refused to yield its colour. The Egyptians were not a civilization that accepted defeat easily. Faced with the inadequacy of ground lapis lazuli as a pigment, and the desperate need for blue across the entire apparatus of their religious and decorative art, they did something remarkable. They invented the world's first synthetic pigment. Egyptian blue, known in their own language as kesbej irtiu, meaning artificial lapis lazuli, was created by heating a precise mixture of sand, copper minerals, calcium carbonate and an alkali-like natron to temperatures between 850 and 1000 degrees Celsius. The result was a blue glassy material that could be ground into a powder and used as a durable, brilliant blue pigment. Its chemical formula is KCuSi4O10, calcium copper silicate, also known as cuproavaite. Egyptian blue is the world's oldest known synthetic pigment. It originated in Egypt over 5,000 years ago, around 3300 BCE. This was a phenomenal achievement for the time. The synthesis required understanding precise ingredient ratios. Too much lime turned the product green. Too much alkali changed the texture. The wrong temperature either failed to complete the reaction or destroyed the resulting compound at temperatures above 1050 degrees Celsius. There was no periodic table, no chemistry textbooks, no formal understanding of stoichiometry or reaction mechanisms. The Egyptians figured this out entirely through empirical trial and error, eventually arriving at a recipe so consistent that they could produce Egyptian blue in industrial quantities and trade it across the ancient Mediterranean world. They also desired to imitate the semi-precious stones, turquoise and lapis lazuli, which were valued for their rarity and stark blue colour. Use of naturally occurring minerals such as azurite to acquire this blue was impractical, as these minerals were rare and difficult to work. Egyptian blue was a miracle material in its time. It was chemically stable. Unlike organic pigments, it did not fade with exposure to light or moisture. It retained its blue colour for thousands of years. It was relatively inexpensive to produce compared to lapis lazuli. And it was versatile. It could be ground fine or left coarse, used as paint on stone, wood, plaster, papyrus or canvas, or shaped into beads, figurines and inlays. It was used throughout Egypt and exported to Mesopotamia, Persia, Greece and Rome. Fascinatingly, in 2006, scientists discovered that Egyptian blue glows under fluorescent lights, indicating that the pigment emits infrared radiation. This property, luminescence in the near-infrared when excited by visible light, is unique among ancient pigments and has revolutionized the ability of modern art historians to identify Egyptian blue on ancient artifacts, even where the visible blue colour has faded or been obscured. But Egyptian blue was not destined to last. With the fall of Rome and the collapse of the trade networks and technological knowledge that supported its production, the recipe was lost. Medieval Europe's artisans had no Egyptian blue, and they had no reliable supply of anything else that could easily produce blue at reasonable cost. They were left with only a handful of inadequate options: azurite, indigo, woad, each with significant problems. Azurite is a naturally occurring copper carbonate mineral with a deep blue colour, but it is chemically unstable. Azurite pigment is unstable in air and would eventually be transformed into its green counterpart, malachite. Medieval paintings made with azurite often have patches of green where the blue has chemically degraded into its sister mineral, a disaster for any artist trying to depict the sky or sacred blue robes. Indigo and woad could dye textiles, but translating them into a durable paint pigment was technically difficult and produced colours that faded in oil. Which brings us back to lapis lazuli and to the story of ultramarine, the most extraordinary chapter in the history of blue pigment. Natural ultramarine, made from ground and purified lapis lazuli, was different from the dull greyish powder you get by simply grinding the stone. Through an elaborate, painstaking process developed by medieval craftsmen, the blue lazurite crystals could be separated from the contaminating calcite and pyrite, yielding a pigment of deep, brilliant, almost supernatural blue intensity. The process involved mixing powdered lapis lazuli with pine resin, mastic, and wax or oil heated together, kneading this dough-like mass, then soaking and squeezing it in a lye solution. The lazurite particles would gradually wash out of the mass into the lye, while the contaminating minerals stayed embedded in the resin binder. Multiple extractions, each one producing a purer, more intensely blue fraction, could eventually yield a pigment of extraordinary quality. This process was incredibly laborious. Its lengthy grinding and washing process makes the natural pigment quite valuable, roughly 10 times more expensive than the stone it comes from. The lapis lazuli itself, remember, had to travel from a single mine in northeastern Afghanistan to workshops in Venice or Florence. A journey of thousands of kilometres through trade routes controlled by middlemen who extracted premiums at every stage. The word ultramarine comes from the Latin ultramarinus, meaning beyond the sea, a reference to the distant origins of this precious commodity. Between the 14th and 15th centuries, it was as expensive as gold in Europe. Not comparable to gold, not almost as expensive as gold, literally as expensive as gold, measured by weight. For Renaissance painters working in the 14th, 15th and 16th centuries, natural ultramarine was the most expensive material in their studios, more expensive than their paints made from gold leaf, more expensive than the finest pigment reds made from crushed semi-precious stones. Ultramarine was the finest and most expensive blue used by Renaissance painters. It was often used for the robes of the Virgin Mary and symbolized holiness and humility. When Raphael painted the blue of the Madonna's mantle, when Titian used that deep, resonant blue in his masterpieces, when Vermeer created the paintings we now associate with his name and his signature colours. They were using material more precious, weight for weight, than the gold they might have used for frames. This is not merely an economic footnote, The scarcity and cost of blue physically shaped what art was made and what it was permitted to depict. Artists' contracts sometimes specified which figures were to be painted in ultramarine. Only the most central and sacred figures could wear the most precious blue. Lesser figures would be painted in cheaper azurite or smalt, both more affordable and noticeably less vivid. The hierarchy of colour was literally a hierarchy of divinity, encoded in the price of pigments. In fact, during the Renaissance, it is reputed to have been more expensive than gold, and, as a result, often reserved for the pictorial representations of the Madonna and Christ. Vermeer, in particular, seems to have been so enamoured of blue that he used natural ultramarine with extraordinary generosity in his paintings, contributing, it is thought, to the financial struggles he faced throughout his life. X-ray fluorescence analysis of paintings like Girl with a Pearl Earring and Woman in Blue, Reading a Letter, has revealed that Vermeer used ultramarine in quantities that contemporary painters of his time and financial circumstances almost never risked. In the dental tartar of medieval nuns and scribes who worked on illuminated manuscripts, researchers have found traces of lapis lazuli, probably acquired by licking their brushes while applying ultramarine to sacred texts. The blue of heaven was quite literally entering their bodies as they painted its symbolic representation. The desperation to find an affordable substitute drove chemistry for centuries. When Egyptian blue was rediscovered in the early 19th century by the chemist Humphrey Davy, who analysed ancient artefacts and identified the copper silicate composition, it sparked intense interest but no practical revival. The material, while superior to alternatives in stability, was technically difficult to match with Renaissance quality ultramarines, depth and purity. The next major chapter happened by accident in a paint shop in Berlin in the early 1700s. A colour maker named Johann Jakob Diesbach was attempting to synthesize a red pigment, cochineal lake, using potash that had been contaminated, unbeknownst to him, with blood. The iron from the blood reacted with the other ingredients to produce, instead of red, an intense blue compound, iron ferrocyanide, which became known as Prussian blue. But it wasn't until the early 1700s that another synthetic blue pigment was discovered, this time accidentally, by a paint maker from Berlin who, while attempting to make a red dye, unintentionally used blood-tainted potash in his recipe. The iron from the blood reacted with the other ingredients, creating a distinctly blue compound, iron ferrocyanide, which would later be named Prussian blue. Prussian blue was a genuine revolution. It was affordable, relatively light-fast, though not perfectly so, and could be produced in large quantities. It became one of the most widely used blue pigments of the 18th and 19th centuries. Pablo Picasso used it almost exclusively during his blue period, those haunting paintings of poverty and loneliness that define one of the most discussed phases in the history of art. Katsushika Hokusai used it to produce his iconic woodblock print, The Great Wave, of Kanagawa, one of the most reproduced artworks in human history. The deep, rich, oceanic blue of that print is Prussian blue. And in 1842, the astronomer John Herschel discovered that Prussian blue had unique photosensitivity. It darkened on exposure to light, a property that made it the foundation of cyanotype photography and, most practically, the architectural blueprint, a technology that transformed the documentation of designed structures for a century. But the search for synthetic ultramarine, a material that could match the depth, brilliance and purity of natural lapis lazuli at a fraction of the cost, continued. It was finally solved in 1826, independently and almost simultaneously, by the French chemist Jean-Baptiste Guimet and the German chemist Christian Gmelin, who both found that heating clay, sodium carbonate, sulfur and carbon together at high temperatures produced a material chemically identical to the lazurite in lapis lazuli. It remained an extremely expensive pigment until a synthetic ultramarine was invented in 1826. The synthesis worked because the key chromophore in lazurite, the component that produces its blue colour, is a radical anion of sulfur, specifically the trisulfide radical S3, in which an unpaired electron is delocalized across 3 sulfur atoms. This unusual electronic configuration absorbs light in the red and orange range and reflects the blue and violet wavelengths, producing ultramarine's characteristic deep blue. Getting sulfur into precisely this radical anionic state, embedded in the right crystal structure, requires the very specific conditions of high-temperature synthesis in an aluminosilicate zeolite host, exactly the conditions Guimet and Gmelin found. Synthetic ultramarine was in many ways more beautiful than its natural counterpart. Synthetic ultramarine is a more vivid blue than natural ultramarine because the particles of synthetic ultramarine are more finely divided and uniform and contain fewer impurities than natural ultramarine or lapis lazuli. By the mid-1800s, the price of blue had collapsed. Ultramarine, once traded ounce for ounce against gold, became affordable enough for everyday use. The consequences were immediate and visible in art. Suddenly, blue appeared everywhere in paintings, wallpapers, ceramics, and textiles that had previously been restricted in their use of blue by sheer cost. The story of synthetic blue dyes in the 20th century added one more chapter with the development of phthalocyanine blue in 1928. A copper-based organic pigment of extraordinary tinctorial strength, brightness and chemical stability that became the most widely used blue pigment in commercial paints, inks and plastics. It is probably the most produced synthetic blue colorant in the world today, found in everything from packaging to spacecraft livery. But it had to be designed and synthesized in a chemical laboratory. Nothing in the biological world ever produced anything like it. Part 6. Blue in the Animal World. A rogue's gallery of extraordinary cases. While the broad pattern is clear, blue is rare in nature, mostly achieved through structural optics rather than pigment chemistry. There are some extraordinarily interesting exceptions and edge cases that illuminate just how far life will go to achieve this elusive colour when natural selection demands it. The poison dart frogs of Central and South America are among the most strikingly blue animals in existence. Species like Dendrobates tinctorius and Ufaga pumilio display blues of such electric intensity that they seem almost fluorescent. These frogs genuinely do produce pigmentation. Their blue and black or blue and red coloration functions as aposematic warning coloration, telling predators that the frog is chemically toxic and should not be eaten. The cost-benefit calculation is different from most organisms. For an animal whose survival depends on being noticed and recognized as dangerous, the metabolic cost of producing rare, difficult-to-make pigments is worth paying. The actual source of the blue component in many poison dart frogs involves a combination of yellow carotenoid pigments in the skin's xanthophore cells and blue scattering structural color from iridophore cells containing guanine crystals. The interaction between the yellow pigment layer and the blue structural color layer produces, in some species, green, blue plus yellow-green, as per additive color mixing. In the blue and black pattern species, the yellow pigment is absent or reduced in the blue patches, allowing the structural blue to appear directly. This multi-layered, multi-mechanism system is another testament to how hard life works to achieve blue when the evolutionary pressure exists. Butterflies, other than Morpho, have taken remarkably different approaches to blue. The small hair-streaked butterflies of the genus Calophrys produce their green or blue-green coloration through three-dimensional photonic crystal structures inside their wing scales, gyroid photonic crystals, three-dimensional bicontinuous networks of chitin and air that produce structural color through a fundamentally different mechanism from the Morpho's two-dimensional lamellae. These gyroid structures are among the most complex three-dimensional nanoscale architectures found in any biological system, and their development requires an extraordinary degree of control over the self-assembly of biological membranes during the pupal stage of development. Peacocks, which appear to display blue in their iridescent tail feathers, are using yet another variant of structural color, a two-dimensional photonic crystal of melanin granules, arranged in precise arrays within the feather barbules. The spacing of the melanin granule arrays determines the reflected color. Blue arrays are spaced differently from green ones, and the mix of blue and green barbels across a single feather creates the shimmering, multicolored display for which peacocks are justifiably famous. Careful examination of peacock feathers under a light microscope reveals that there is no single color in a feather. Rather, different barbule cells are arranged to reflect different wavelengths, and the overall blue-green iridescence is a mosaic of structural colors at a scale below the resolution of the naked eye. The kingfisher, that jewel of European and Asian streams, the bird that inspired the term iridescent, achieves its brilliant blue back through a thin film interference mechanism in its feather structure. Unlike the blue jay, which uses a quasi-random spongy nanostructure to scatter blue, the kingfisher's feathers employ more ordered multilayer nanostructures that produce not just blue, but angle-dependent iridescent blue, the color that flashes and shifts as the bird moves in flight, creating the sensation of an animate sapphire. In the ocean, the blue-ringed octopus produces its terrifying warning coloration, those electric blue rings that flash as a warning sign before a bite that can kill a human in minutes. Through iridophores, cells that contain thin films of reflectin protein arranged in precise multi-layer stacks. The reflectin proteins are unique to cephalopods and represent an independent evolutionary invention of thin-film optics. The blue of the warning rings can be activated by muscular contractions that change the thickness of the reflectin layers, physically tuning the thin film interference to produce the warning blue on demand. Blueberries and other blue fruits present a particularly interesting case. When you look at a blueberry, you see blue or blue-purple. But the pigment responsible for the colour, anthocyanin, is actually deep red in concentrated solution. So why does the fruit look blue? The answer is a combination of the anthocyanins' shift toward blue-violet at the slightly alkaline vacuolar pH of the blueberry cell and, crucially, a waxy surface coating called bloom, a thin film of epicuticular wax that produces structural colour effects on the surface of the fruit. Research published in 2024 demonstrated that artificially removing the wax bloom from blueberries causes them to appear much darker and redder, revealing that the wax structural colour is a major contributor to the characteristic blue-grey perception. The blueberry's blue is, in part, a nanoscale optical trick in a wax layer. Even the blue of the sky, magnificent and pervasive as it is an illusion built from physics rather than pigment. Blue photons scattered by molecules of air rather than produced by any blue pigmented material. The ocean appears blue partly by reflection of the sky and partly because water itself absorbs red light more strongly than blue. But the ocean contains no blue pigment. Pure water in large enough volume actually is very slightly blue for exactly this absorption reason, but rivers and shallow coastal waters are blue primarily because they mirror the sky. This accumulation of cases, birds, butterflies, frogs, octopuses, berries, sky, eyes, ocean, builds to a single, remarkable conclusion. Blue in the natural world is almost universally an optical performance rather than a chemical property. Life has repeatedly found it easier to build complex nanoscale optical machinery than to evolve a stable blue molecule. The machinery is expensive to build and requires exquisite genetic control over the self-assembly of cell structures at nanometer precision. But it works. The chemistry simply doesn't. Part 7. The physics problem. Why blue light was impossible to make electrically. The rarity of blue in nature sets the stage for what may be the most dramatic chapter in the story of blue. The 3-decade struggle to create blue light artificially using semiconductor technology, a struggle that ended only in 1993, won by a single engineer working against the consensus of his entire field. To understand why blue LEDs were so hard to make, you need to understand how LEDs work at all. A light-emitting diode is a semiconductor device that produces light through electroluminescence, the direct conversion of electrical energy into photons. When an electric current flows through a semiconductor material, electrons moving from higher to lower energy states release the energy difference as photons of light. The wavelength of the emitted light, its color, is determined by the band gap of the semiconductor material. The energy difference between the conduction band, where electrons are free to move, and the valence band, where they are bound. Different semiconductor materials have different band gaps. A semiconductor with a small band gap produces photons of low energy, long wavelengths, which means infrared or red light. A semiconductor with a medium band gap produces green or yellow. A semiconductor with a large band gap produces blue or ultraviolet light, because blue photons carry much more energy than red ones. The challenge of blue LEDs was the challenge of finding and fabricating a semiconductor material with just the right large band gap, and then figuring out how to dope it, introduce controlled impurities, to create the p-type and n-type layers needed for a functioning p-n junction. Red LEDs were made in the early 1960s based on gallium arsenide and gallium arsenide phosphide, materials well understood and relatively easy to work with. Green LEDs followed in the late 1960s. Both materials had band gaps corresponding to their respective colours and could be doped into p-type and n-type forms without enormous difficulty. Blue LEDs proved to be much more difficult to create than red and green diodes. Despite considerable efforts both in the scientific community and in industry, the blue LED had remained a challenge for 3 decades. The difficulty was not for lack of candidates. 2 semiconductor materials had the right band gap for blue light: zinc selenide, ZnSe, and gallium nitride, GaN. Gallium nitride was considered a dead end. The hard material had to be layered onto a sapphire substrate, which left defects in the crystal lattice. Billions of defects. Because defects impede the motion of electrons, that was a problem. Zinc selenide is a softer material with 6 orders of magnitude fewer defects, so it's not surprising that all the big companies thought they'd find success creating blue light with it. Throughout the 1970s and 1980s, virtually every major electronics company and academic laboratory working on blue LEDs concentrated on zinc selenide. IBM, Sony, Philips, RCA, the biggest names in the industry, poured resources into ZnSe research. The reasoning was solid. ZnSe had far fewer crystal defects than GaN, and it was known that crystal defects in semiconductors act as non-radiative recombination centers, traps that capture electrons and holes and convert their energy to heat instead of light. Fewer defects should mean more efficient light emission. Meanwhile, gallium nitride was the road not taken. Its problems seemed insurmountable. GaN could only be grown as a thin film deposited on a substrate of a different material, and no perfectly lattice-matched substrate existed. Every available option left the GaN crystal with an enormous density of defects at the interface, propagating throughout the crystal. The material was hard to dope into p-type form. It was refractory. It required extremely high temperatures to work with. Almost everyone in the field agreed. GaN was a dead end. Almost everyone. Not Isamu Akasaki. Akasaki was a professor at Nagoya University in Japan who had been working on GaN since 1974, a lonely vigil through years when the rest of the field abandoned the material. In 1986, working with his doctoral student Hiroshi Amano, Akasaki found a way to grow GaN with dramatically improved crystal quality using a technique called metal-organic vapor phase epitaxy, MOVPE, and a low-temperature buffer layer. The buffer layer of aluminum nitride, deposited at low temperature before the main GAN growth, smoothed out the substrate surface and reduced the defect density enough to allow higher quality GAN crystal growth. In 1989, Akasaki and Amano achieved the critical breakthrough of p-type GAN doping. In a semiconductor LED, you need two types of material: N-type, with extra electrons, and p-type, with extra holes, absences of electrons. Getting p-type GAN had been an unsolved problem for years. Akasaki and Amano found that electron beam irradiation of GAN doped with magnesium activated the magnesium dopants to produce p-type material. The mechanism, they later discovered, involved the electron beam generating heat that drove out hydrogen atoms that were otherwise blocking the magnesium acceptor sites, a process called hydrogen passivation removal. Enter Shuji Nakamura. Nakamura felt that Nichia had to develop a product that would not be competing with those of other larger companies. That product would be the blue LED. Scientists had produced LEDs that emitted red or green light, but attempts to make blue LEDs were unsuccessful. Nakamura's supervisor discouraged him by noting that the blue LED had been sought after for decades by much better funded researchers. But Nakamura, after spending a year at the University of Florida to master MOV-PE techniques, returned to Nikkei in 1989 and made a decision that put him in a tiny minority. He chose to work on GAN rather than ZnSe. At the 1992 meeting of the Japanese Society on Applied Physics, Nakamura observed that sessions about ZnSe drew hundreds of people, while the session on GAN had just 4, the speaker, the session chair, and 2 people in the audience, including me. Working 12-hour days, often alone in his laboratory, Nakamura developed 2 critical innovations that unlocked GAN for blue LEDs. The first was a 2-flow MOCVD reactor, a modification of the standard crystal growth apparatus that used a horizontal gas flow to carry the GAN precursor compounds over the heated substrate, and a vertical flow to push the reactants toward the substrate surface. This modification dramatically improved the uniformity and quality of the GAN films. The second was his breakthrough on p-type GAN. Reading Akasaki and Amano's paper on electron beam activation of magnesium-doped GAN, Nakamura reasoned that if the electron beam was working through the heat it generated, then simply annealing, heating, the magnesium-doped GAN in nitrogen atmosphere should achieve the same result, and much more cheaply and easily than electron beam treatment. He tried thermally annealing magnesium-doped GAN films, which effectively boiled off hydrogen atoms, hydrogen passivation, activating the hole-donating magnesium. This simple, cheap method was perfect for the production line, and it also produced p-type GAN with a higher concentration of holes. He was right. Thermal annealing worked beautifully, and it worked at a scale and cost that electron beam treatment never could. This single insight, recognizing that what the electron beam was really doing was generating heat, and that heat alone could do the job, transformed the fabrication of p-type GAN from a laboratory curiosity into an industrial process. But there was still the problem of getting the right color. Nakamura's first blue LED, which glowed for a record-setting 1,000 hours, was too violet. It needed an indium alloy to produce light of a longer, bluer wavelength. Adding indium to the GaN to form indium gallium nitride, InGaN, allowed Nakamura to tune the band gap and shift the emission wavelength from violet toward true blue. By adjusting the proportion of indium in the InGaN alloy, he could dial in the exact wavelength of emission. In 1993, Nakamura produced a blue LED that was not merely technically a blue LED, it was brilliantly, blazingly, practically useful. What made his blue LED special was that it was nearly 100 times brighter than existing blue LEDs at the time. This was not an incremental improvement. It was a transformation so dramatic that it essentially created a new technology from scratch. The world changed. When Isamu Akasaki, Hiroshi Amano, and Shuji Nakamura produced bright blue light beams from their semiconductors in the early 1990s, they triggered a fundamental transformation of lighting technology. Red and green diodes had been around for a long time, but without blue light, white lamps could not be created. The logic is inescapable. White light is a mixture of all visible wavelengths. To create white LED light, you need LEDs of all three primary colors. Red and green had existed for 30 years. Without blue, white LED light was impossible. Nakamura's blue LED was the missing third piece of a puzzle that had been incomplete for 3 decades. By coating a blue LED with a yellow phosphor that absorbed some of the blue photons and re-emitted them at yellow wavelengths, Nikia produced white LED light, bright, efficient, reliable, long-lasting white LED light that has since displaced incandescent and fluorescent lighting as the dominant artificial light source in the world. The most recent record is just over 300 lumens per watt, which can be compared to 16 for regular light bulbs and close to 70 for fluorescent lamps. As about 1/4 of world electricity consumption is used for lighting purposes, the LEDs contribute to saving the Earth's resources. Materials consumption is also diminished as LEDs last up to 100,000 hours, compared to 1,000 for incandescent bulbs and 10,000 hours for fluorescent lights. One man's stubbornness in betting on GaN when the entire industry was convinced the answer lay in Z inertia. Powered by intuition, technical insight, and an almost pathological willingness to keep working when everyone else had given up, produced a technology that now saves an estimated 500 million tons of CO2 per year compared to the lighting it replaced. Every LED screen you look at today, your phone, your laptop, your television, relies on blue LEDs as one of its 3 sub-pixel color sources. Every LED white light source in every home, office, street and vehicle on Earth owes its existence to the invention Nakamura made in that small company in rural Japan. The Nobel Prize recognized Nakamura for the invention of efficient blue light-emitting diodes, which has enabled bright and energy-saving white light sources. It is rare that a Nobel Prize in physics goes to something so directly, immediately, transformatively useful. The committee was explicit. This was an invention of the greatest benefit to mankind. Nakamura's reward from Nikia, his employer, an initial bonus of $120,000, approximately $180. He later sued for $2 billion and eventually settled for $840 million in a settlement after Nietzsche's appeal. The story of Shuji Nakamura is not only a story about the physics of blue light, it is also a story about what happens when an individual's creative stubbornness drives forward against institutional inertia, and what happens when a society undervalues the people it most depends upon. Part 8. The Evolution of Blue. Why natural selection struggled with the hardest colour. If we step back from the human story and return to the natural world, the question that hangs over everything is, why hasn't evolution solved the blue problem better? Life has had over 3.5 billion years of continuous experimentation. It has evolved eyes, brains, echolocation, photosynthesis, the immune system, and the genetic code. Why hasn't it produced a reliable, common, stable blue pigment? The answer requires thinking carefully about how evolution actually works, not as a designer working toward a goal, but as a blind process of variation and selection, operating only on what exists, never looking ahead, never planning. Pigment molecules evolve through gradual modification of existing metabolic pathways. The biosynthetic pathways for red, orange and yellow pigments in plants, the carotenoid pathway and the anthocyanin pathway, are among the oldest and most biochemically fundamental in plant biochemistry. They evolved early, are deeply integrated into central plant metabolism, and are highly conserved across most plant species. Mutations that modify these pathways can shift colours. More or fewer hydroxyl groups on the anthocyanin B ring shift the colour between red and purple. Adding acyl groups shifts it further toward blue-violet. But every step toward blue is a step away from chemical stability, because the molecular features that shift colour toward blue also tend to make the molecule more reactive and more vulnerable to degradation. The evolutionary landscape of colour chemistry is asymmetric. Moving from red pigments toward orange is a small molecular step and produces molecules that are still relatively stable. Moving from red toward blue requires large structural changes, adding hydroxyl groups, acyl groups, sugar moieties, metal binding sites, each of which adds metabolic complexity and reduces stability. Each step creates a pigment that is harder to synthesize, requiring more enzymatic steps, more energy, more genetic infrastructure, and easier to destroy, more sensitive to pH, oxygen, heat, light. The evolutionary cost grows with each step, while the selective benefit, attracting pollinators that prefer blue or signaling toxicity or sexual selection, is often modest and context-dependent. For animals, the problem is even more acute. Most animal pigments are not synthesized de novo, but acquired from food. Carotenoids, the yellows and oranges and reds, come from plants. Melanin, the black and brown, is synthesized from the amino acid tyrosine through a relatively simple enzymatic pathway. But there are no dietary sources of blue. The blue that a bird's feathers might acquire from eating blueberries is destroyed in digestion. The anthocyanin pigment is broken down before it can be incorporated into feather tissue. The metabolic pathway for manufacturing blue pigments from scratch doesn't exist in animal cells, because it was never evolved, because there was never a dietary shortcut that could have seeded the necessary enzymatic machinery. The evolution of structural colour sidesteps this problem brilliantly but expensively. Building nanostructures requires precision biological manufacturing at scales that push the limits of what cell biology can control. The self-assembly of the morpho-butterfly's nanolamellae, the gyroid photonic crystals of calliferous butterflies, the amorphous sponge structures of blue bird feathers, each of these requires the precisely regulated expression of structural proteins, the tightly controlled spatial and temporal dynamics of cell development, and a genetic regulatory network of considerable complexity. Evolving these structures from scratch is not easy, and yet, as we have seen, evolution has done it dozens of times. Why? Because when selection pressure for blue is strong enough for mate attraction, predator warning, or species recognition, the payoff justifies the metabolic investment. The morpho butterfly's blue is not just pretty. It is believed to function in both intraspecific communication, potentially mate recognition or territorial display, and in the dazzling, confusing effect the flashing blue wings have on predators, which makes the butterfly's erratic flight harder to track. The evolution of structural colour has itself been illuminated by recent advances in molecular biology. Advances in molecular genetic tools such as CRISPR, in addition to much improved resolution of microscopy techniques, have provided tantalizing new insights into the evolution and development of optical nanostructures in butterflies. Butterflies have evolved a diverse suite of optical nanostructures to produce vivid displays of structural color. Research using CRISPR gene editing has allowed scientists to knock out specific genes in butterfly wing development and observe how the nanostructures change, connecting specific genetic instructions to specific nanoscale architectural features for the first time. This work is opening up the genetics of structural color and revealing how deeply the developmental machinery for building these optical structures is embedded in the genetics of these animals. The evolutionary history of blue structural color also tells us something important about the relationship between color and perception. The animals that have evolved the strongest blue coloration are almost all animals in visual environments and in ecological contexts where colour signalling matters intensely. Butterflies in rainforest clearings, where light is bright and complex, birds in open habitats where long-distance colour recognition is important, poison frogs in tropical forests where the warnings need to be unmistakable. This is not a coincidence. Natural selection for blue coloration is correlated with selection in the visual systems of both the signalling organism and its observers. Co-evolution between coloration and vision drives the development of both. Blue was absent in the first Paleolithic cave paintings. Those depictions were made using reds, yellows and blacks of all hues, but no blue. This absence from prehistoric art is particularly evocative. Paleolithic artists were extraordinarily sophisticated. They depicted animals with dynamic accuracy, used three-dimensional contours of cave walls to suggest depth, and mixed pigments to create subtle colour gradations. They painted with ochre, charcoal and manganese oxides because those were the natural materials available. They had no blue pigment because, as we have seen, the natural world offered none that was stable, plentiful and easily workable. Part 9. The language of blue, the curious case of ancient minds and a missing colour. There is one more dimension to the rarity of blue that deserves serious discussion, because it takes us from physics and chemistry into the territory of cognitive science and the history of human perception. The question of whether ancient humans even perceived blue the way modern humans do. This is a genuinely strange and controversial claim, but the evidence for it is substantial and worth examining carefully. Some scientists have proposed that the earliest humans were colourblind in the sense of lacking a conceptual category for blue. The evidence is linguistic. Ancient languages are remarkably consistent in having no word for blue. The British politician and scholar William Gladstone, later 4-time Prime Minister of Britain, conducted an exhaustive analysis of colour references in the works of Homer, the ancient Greek poet who composed the Iliad and the Odyssey in approximately the 8th century BCE. These are enormous works containing thousands of colour descriptions of sea, sky, wine, metal, plants and animals. Gladstone found that Homer never once used a word that unambiguously means blue. The sky in Homer is never blue. It is bronze or iron. The sea is wine dark, a phrase that has puzzled classicists for centuries. Violets are described as purple. Blue and black are sometimes seemingly conflated. The linguist Lazarus Geiger subsequently confirmed that this pattern was not specific to Homer, but characteristic of ancient languages generally. In an 1869 analysis, Geiger showed that the ancient texts of Hindu Vedas, the Icelandic sagas, the Quran, and even ancient Chinese writings all lacked a word for blue. He observed a consistent evolutionary pattern in how colour vocabulary develops in languages, across an enormous range of cultures and historical periods. Languages first develop words for black and white, then red, then yellow or green, and last of all blue. Blue was always, everywhere, the final colour to receive its own dedicated word. The cognitive scientist Jules Davids, and more recently the researcher Brent Berlin and Paul Kay, in their landmark 1969 work Basic Colour Terms, documented this progression systematically across hundreds of languages and found the same hierarchical pattern. Black and white always first, red always before green and yellow before blue, blue before brown, and brown before purple, pink, orange and grey. In the absence of natural blue things to name, and absent a ready-made blue pigment to work with, or a cultural tradition of using blue, there was no practical pressure to develop a word for it. The philosopher Ludwig Wittgenstein famously argued that language shapes perception, that categories you lack words for may be genuinely harder to perceive distinctly. Modern research in colour cognition supports a modified version of this claim. People who speak languages with more fine-grained colour terminology can distinguish between colours more quickly and accurately in the category boundaries defined by their language. The Piraha people of the Amazon, whose language has only terms for light and dark, have significantly different colour perception in experimental tests compared to English speakers. The Himba of Namibia, whose colour vocabulary carves up the spectrum very differently from English, show exactly those category boundaries in their perceptual discrimination tasks. This does not mean that ancient people were literally blind to the colour blue in the physical sense. They had the same cone cells and visual processing hardware as we do. But it suggests that the cognitive category of blue, the recognition of blue as a distinct, nameable experience quality, may have been less vivid and less salient to people who lived in a world with no blue pigment, no blue paint, no blue in their art, and almost nothing truly blue in the living world around them. Colour is a blend of science, culture, and even philosophy. Because the object, the cornflower, it looks blue to me, but that's because it absorbs red light. In what sense is that blue? And also it appears blue to me, but an animal that doesn't have the same receptors as us is going to see it in a different colour. So, is blue real? The rarity of blue in nature, in this interpretation, had cognitive consequences. Humans evolved in a world where red was everywhere, blood, fruit, fire, where yellow and orange and green filled the landscape, earth, grass, leaves, where black and white were the extreme contrasts of light and shadow. But blue, saturated, pure, true blue, was almost nowhere in the lived biological environment. It was in the sky, but the sky is not an object. It was not in animals, not in plants, not in soil, not in food, not in shelter materials. For the purposes of object recognition and identification, blue was simply not a useful category to have finally developed. When humanity acquired blue, when Egyptian blue gave artisans their first synthetic pigment, when lapis lazuli became a trade commodity, when indigo transformed textile dyeing, something shifted not just in what was made, but in how the colour was perceived and valued. Having blue opened up a cognitive space for blue. Having words for blue, having blue objects, having blue in art and symbolism, these things made blue real in the full cultural and cognitive sense in a way it had never been before. Part 10. Blue in the modern world, from scarcity to ubiquity. The story of blue reaches its contemporary chapter in a world that would be unrecognizable to any artist of the Renaissance, any engineer of the 1980s, any ancient Egyptian priest. Blue is no longer rare in the human world. It has become perhaps the most ubiquitous colour in the human visual environment. The explosion of blue in modern life is the direct consequence of the technological breakthroughs we have traced. Synthetic ultramarine democratized blue in paint. Prussian blue and phthalocyanine blue made blue ink affordable. Indigo synthesis, achieved chemically in 1880 by Adolf von Baeyer, for which he received the Nobel Prize in Chemistry in 1905, ended the reliance on plant-derived indigo and made blue denim fabric available globally, creating the most widely worn garment in human history, blue jeans. The blue LED made blue screens possible and blue light universal. Today, blue is the most popular colour in global preference surveys, consistently chosen as favourite colour by between 26% and 40% of respondents across most cultures. This preference may itself be a product of the cultural and technological transformation we have traced. Blue became available, blue became common, blue became associated with sky and water and calm and trust through centuries of cultural conditioning, and now most humans, asked to name a colour they love, reach for blue. The blue of digital screens, the blue subpixels in every LCD and OLED display, are blue LEDs, either directly in OLED displays or filtered blue light from a white LED backlight through a blue color filter. The specific wavelength of display blue, around 450 to 460 nanometers, was chosen to maximize color gamut while working within the physics of available semiconductor materials. Nakamura's GAN blue LEDs, in their InGaN form, naturally emit at wavelengths right in this range. This has created a new scientific and public health conversation about blue light exposure from screens. Because blue light photons carry more energy than red or green, they are capable of reaching and potentially affecting the retinal cells at the back of the eye more aggressively than longer wavelengths. Research in this area is ongoing and contested, but there is solid evidence that blue light in the evening hours suppresses melatonin production through its effects on the intrinsically photosensitive retinal ganglion cells that regulate circadian rhythm, disrupting sleep. The same properties that make blue light so valuable for screen displays, its short wavelength and high energy, make excessive evening exposure to it a genuine physiological concern. Blue light also has applications in medicine, particularly in photodynamic therapy, where specific wavelengths of blue or near blue light are used to activate photosensitizing compounds in cancer treatment and in phototherapy for neonatal jaundice, where blue-green light breaks down bilirubin in the skin of newborn babies with hyperbilirubinemia. The structural colour research, inspired by morpho butterflies and bluebird feathers, has generated a growing field of bio-inspired photonic engineering. Scientists at institutions ranging from MIT to the University of Cambridge have used the principles of morpho-wing nanostructure to design structural colour pigments that do not require conventional dyes. These structural colour materials, whether made from cellulose nanocrystals, block copolymers, colloidal arrays, or nanofabricated metallic or dielectric thin films, produce colours that cannot fade because there is no dye to degrade. The colour is in the geometry, and the geometry is stable as long as the material is intact. Applications being developed include cosmetics that produce structural blue without synthetic dye, anti-counterfeiting structures for banknotes and security documents, colour filters for cameras and sensors, and decorative coatings for vehicles and electronics. The butterfly, in a sense, is teaching human technology how to do what chemistry cannot, to make reliable, stable, non-fading blue by building the right architecture at the right scale. Research into the genetics of structural colour in butterflies has taken on new dimensions with the advent of CRISPR gene editing. By modifying specific genes involved in wing-scale nanostructure development, scientists can now create butterflies with altered structural colours. Shifting blue scales toward green or white, or creating unusual iridescent patterns not found in nature. This work, beyond its basic scientific interest, is generating insights into the developmental biology of nanostructure assembly that could eventually be applied to guide the self-assembly of structural color materials in industrial processes. In contrast to the way people currently mimic naturally occurring structural colors, by using industrial processes to deposit layers of heavy metals by electricity that's expensive and energy-intensive. Butterflies and moths have evolved a way to create these stunning colors with a string of sugar molecules. They appear to be the basic components of all animal cells. The genetic program controlling the creation of the nanostructures is elegant, robust, and done in a way that is not hazardous to the life of the animal. If we can figure out how the butterflies do what they do, we have the potential to apply what we learn to a vast array of problems, like creating cars that have their paint grown from the surface of their sheet metal, vivid cosmetics that are inherently safe for use with minimal testing, and even making solar cells more efficient. The quest for blue in food coloring remains one of the few areas where natural blue is still genuinely difficult to provide. The food industry uses synthetic blue dyes, FD&C Blue No. 1, Brilliant Blue, and FD&C Blue No. 2, Indigo Carmine, in the United States, and Patent Blue V in Europe for food coloring. These are synthetic compounds with no natural analogue, approved after safety testing, but subject to ongoing scrutiny. Choices of blue food colorants are extremely limited. The food industry is investing heavily in finding naturally derived replacements, with limited success to date. Natural blue colorants from food sources, the anthocyanins from blueberries, purple sweet potatoes, and butterfly pea flowers, are chemically unstable, changing color with pH and fading with heat, light, and oxygen. Providing natural blue color to food that will be processed, stored, and consumed is an unsolved problem that the food industry spends significant resources trying to address. The butterfly pea flower, Clitoria ternatea, has attracted particular attention as a natural blue colorant source, because it contains a remarkably complex polyacylated anthocyanin called ternatin that is significantly more stable than most blue anthocyanins. Its intense blue color changes to purple and then pink as pH increases, a property used decoratively in cocktails and teas. But this very pH sensitivity makes it problematic as a food dye that needs to hold its color across varying processing conditions. Part 11. The deepest lesson. What blue teaches us about the universe. We have travelled a great distance in this documentary, from the physics of photons to the molecular chemistry of anthocyanins, from the nanoarchitecture of butterfly wings to the semiconductor physics of gallium nitride, from the mines of ancient Afghanistan to the laboratory of a stubborn engineer in rural Japan. Let us now stand back and consider what all of this reveals about the nature of reality. Blue is rare because it is expensive. That statement applies simultaneously at the level of quantum mechanics, molecular chemistry, evolutionary biology, and human economics, and the consistency of the theme across all these different scales is profoundly illuminating. At the quantum level, blue photons are expensive because they carry more energy than other visible photons. Emitting a blue photon requires a larger energy transition than emitting a red one. Reflecting blue photons without absorbing them requires a molecular or structural system that has precisely the right characteristics. This energetic cost at the photon level propagates up through every level of organization above it. At the molecular level, blue pigments are expensive because the chemical architectures that stably produce blue, the sulfur radical anions of lazurite, the complex metal chelates of metalloanthocyanins, the extended conjugated systems of synthetic dyes, are either not available from the building blocks that life's chemistry provides, or require such elaborate multi-step synthesis pathways that the metabolic cost is prohibitive for organisms without strong selection pressure. At the evolutionary level, structural color is expensive because building and maintaining nanoscale optical architecture requires precise genetic control and developmental precision that goes far beyond what simpler pigment systems demand. The morpho butterfly's wing nanostructure is not just a beautiful accident. It is a complex evolved engineering solution to a problem that chemistry couldn't solve, requiring millions of years of selection and developmental refinement. At the cultural and economic level, blue was expensive for millennia because the natural world provided so little of it, and the technological challenges of synthesizing it were enormous. Lapis lazuli from a single Afghan mine, traded across thousands of kilometers, more valuable than gold. Egyptian blue, the first synthetic pigment in history, invented because the need for blue was so desperate that empirical experimentation over centuries eventually found the recipe. Renaissance painters bankrupted themselves buying ultramarine. 3 decades of failure and hundreds of millions of dollars spent before one engineer working alone cracked the semiconductor physics problem. The consistent theme is that blue costs more to make at every level of organization than any other visible color. It costs more photons worth of energy. It costs more molecular complexity. It costs more evolutionary investment in nanostructure. It costs more human labor, technology, and creativity. The universe seems, in some deep sense, resistant to blue, not through any supernatural agency, but because the physical laws that govern the behavior of light and matter create genuine obstacles to the production and stabilization of blue at every scale. And yet, life finds a way. Evolution finds a way. Human ingenuity finds a way. The morpho butterfly's wings are, in their own way, as extraordinary an achievement as any human technology, a billion-year R&D project that produced, from chitinous protein and air and evolutionary pressure, one of the most beautiful and optically sophisticated structures in the natural world. The ancient Egyptians, without chemistry or physics or periodic tables, discovered through sheer empirical grit how to synthesize the world's first artificial pigment, a blue compound stable enough to survive 5,000 years in burial conditions and still glow with near-infrared luminescence when illuminated today. Nakamura, dismissed by his supervisors, ignored by his field, working alone in a laboratory that most of his colleagues didn't take seriously, produced in 1993 a breakthrough that earned a Nobel Prize, transformed the global lighting industry and created technology that now lights hundreds of millions of homes worldwide. Each of these achievements came not from accepting the rarity of blue, but from refusing to. From pushing against the natural reluctance of the universe to yield this colour, and finding, through millions of years of evolution, through millennia of empirical chemistry, through decades of semiconductor physics, the specific narrow paths through which blue can be reached. The rarity of blue is not just a curiosity. It is a window into the deep structure of physical law, into why energy costs money, why chemistry has constraints, why building things at the nanoscale is harder than building things at the human scale, and why the most beautiful and sought-after things in any domain tend to be the ones that cost the most to make. Part 12. The Future of Blue, What Comes Next. We close with a glimpse at where the science of blue is heading, because the story is not finished, not by any means. In structural colour research, the goal is to achieve what morpho butterflies do, but in scalable, manufacturable form. Several research groups have achieved structural blues using self-assembling block copolymers, materials that spontaneously organize into layered nanostructures with the right dimensions to produce structural color. The challenge is achieving the consistency and uniformity needed for practical application. In 2023, a team at the University of Cambridge reported a method for producing structural colour paints using cellulose nanocrystals, the same material that forms the structural framework of plant cell walls, that self-assemble into films with tunable structural colour. The resulting paints produce colours including blue without any dye, and the colours are, in principle, permanent because there is no chromophore to degrade. In plant biotechnology, genetic engineering has produced truly blue flowers for the first time in species that had never evolved the biochemistry to produce them. A team at the Suntory Company in Japan, working for over 20 years, used genetic engineering to introduce genes for the enzyme flavonoid 3D, 5-hydroxylase, which converts ordinary anthocyanins into delphinidin, into roses and carnations, plants that naturally lack this enzyme and therefore cannot produce blue. Combined with modifications to vacuolar pH and co-pigment chemistry, these engineered plants produce flowers that are blue-violet. Not perfect blue, but the closest any rose has ever come. It was only at the end of the 20th century that genetic engineering was able to create blue flowers, adapted to the markets to meet consumer demands. The next frontier in engineered blue flowers is genuine spectroscopic blue, flowers that reflect at the true blue wavelengths of 450–495 nanometers rather than the violet blue of 400–450. This will likely require not just delphinidin biosynthesis, but also specific metal ion transport into vacuolars, precise pH control, and optimized co-pigment chemistry. A synthetic biology challenge of considerable complexity. In semiconductor physics, research continues on improving the efficiency of GaN LEDs, particularly for the difficult deep blue and ultraviolet range. Beyond LEDs, gallium nitride is now being developed as a power semiconductor material for use in power converters, motor drives, and other high-power electronics. because its wide band gap gives it advantages in high voltage, high frequency, high temperature applications over silicon. The same material that gave us the blue LED is being developed into the transistor technology that may power the next generation of electric vehicles, renewable energy inverters, and 5G wireless infrastructure. Nakamura's material science choice in 1989 continues to yield dividends decades later. In quantum technology, single photons of blue and violet light are being used in quantum communication systems, where the high frequency of blue photons makes them useful for certain quantum information protocols. The same physics that makes blue photons hard to produce, their high energy, also makes them potentially useful for quantum computing applications that require high-frequency electromagnetic signals. And in the most fundamental corner of all, the science of how we see blue, how we perceive blue, how blue is represented in the brain and processed into conscious experience. This remains one of the deep open questions of neuroscience. We can trace the path of blue photons from the sun to the retina, through the photoreceptor proteins to the optic nerve to the visual cortex. But where in that chain does the subjective experience of blue, the qualia of blueness, arise? This is the hard problem of consciousness applied to colour, and it remains as open and as puzzling as the day philosophy first asked it. Blue is still teaching us things about light, about matter, about life, about mind. We began with a simple observation. Look at the living world, and blue is almost absent. We have travelled through chemistry, physics, evolutionary biology, ancient history, and semiconductor engineering to understand why. Here is the full picture assembled. Blue photons carry more energy than any other visible photons, except violet. This energetic richness makes blue simultaneously beautiful and inaccessible. Molecules that absorb the complementary wavelengths to reflect blue must have very specific electronic structures that are hard to achieve in organic chemistry, and even harder to stabilize in the chemical environment of living cells. No organism has ever evolved a dedicated, stable, common, true blue pigment. Every blue flower in the world achieves its color through modification of red pigments, chemical stabilization tricks involving metals and co-pigments, or structural optics, none through a straightforward blue dye. Animals have it worse. They cannot synthesize novel pigments as readily as plants. They have no dietary pathway to acquire blue, and they are therefore forced entirely into structural colour when selection pressure demands blue. And structural colour, while physically elegant, is biologically expensive. It requires building nanoarchitecture at scales comparable to the wavelength of blue light, with precision that pushes the limits of developmental biology. As a result, blue has evolved independently many times across many lineages, but is found in a small minority of species and almost never as a true pigment. It is almost always a physics trick, thin film interference, quasi-amorphous scattering, photonic crystal diffraction, Rayleigh-like scattering, operating at nanoscales that make the blue of the morpho butterfly not just a colour, but an engineering achievement that has spawned entire research fields attempting to replicate it. Human civilization spent 6 millennia struggling with the same problem. The most precious blue material in the ancient world came from a single mine at the other end of the trading world. The first synthetic pigment ever invented, Egyptian blue, made 5,000 years ago, was a direct response to the desperate need for blue that the natural world refused to supply. Natural ultramarine was literally worth its weight in gold for centuries. The science of making blue pigments and dyes drove some of the most important chemical discoveries of the 19th century. And making blue light from electricity, something achieved with red and green by the 1960s, resisted the combined efforts of major corporations and academic laboratories for 30 more years, until a single engineer's stubbornness and insight unlocked the physics in 1993. The blue of the sky is not blue. It is colourless air scattering high-energy photons. The blue of the ocean is not blue. It is water, absorbing long wavelengths. The blue of a blue jay's feather is not blue. It is brown melanin, arranged at nanoscale precision to scatter short wavelengths. The blue of a butterfly wing is not blue dye. It is transparent chitin, built into Christmas tree lamellar nanostructures with a precision that took evolution millions of years to achieve. The blue in your screen is blue photons, produced by indium gallium nitride semiconductors, using physics so challenging that it took human civilization until almost the turn of the 21st century to master. Blue is, in the deepest sense, nature's most reluctant colour. The universe does not hand it over easily. You have to build for it at the right scale, with the right materials, with the precision that demands the highest levels of biological engineering or technological sophistication. When you see blue in the natural world, when a morpho butterfly catches the light and blazes in the rainforest canopy, when a bluebird perches on a branch in morning sun, when a poison dart frog's electric colouring stops you cold, you are not just seeing a pretty colour. You are witnessing the end result of millions of years of nature pushing against one of physics' deepest resistances. You are seeing the universe's hardest colour, hard won. And when you flick on an LED light switch, see your phone screen light up, or look at a blue stripe in a spectrum, you are seeing the triumph of one man and many others before him who looked at that resistance and refused to accept it. Blue is rare because blue is hard, and that is precisely what makes it extraordinary.